Now, I promised to talk briefly about matter waves before going on to properties of matter. Well, not before we're going on to properties of matter, but before we talk about matter waves again in properties of matter. All I really want to say about matter waves is that our understanding of orbitals and shells and all of that is based on this idea that matter has properties like a wave. I mean, we talk about that wavicle, that duality that a particle has, that a subatomic particle has, in that it is a particle, but it is a wave. The truth of the matter is it's always a wave, even when you make an observation on it. If you observe a particle as a particle, the wave in which we talk about, the momentum wave, because both its position, its location, which we normally think of, and its momentum represented by waves. So once you make that observation on that particle's position, you may destroy, and I would do the quotes, but I got a chalk in this hand, you may destroy the wave and only bound it, make it a particle briefly. But that's not true. The truth of the matter is that particle, that electron, that proton, that neutron, that neutrino, whatever we're talking about, at one point has two waves to describe it. It has a momentum wave and it has a positional wave. So you make an observation on that object's position and destroy the wave nature of that particle, but the momentum wave is also there, and that wave has just grown in size. It's just gotten bigger. So when talking about matter waves, we tend to talk about two different kinds of waves. We tend to talk about its positional wave, or well, actually more than two. Its positional wave, its momentum wave, and its energy wave. So when we look at it, we have to realize that wave nature of matter is referring to not what we think of as waves, but the way in which we can describe that particle. So when we look at a probability of a particle, you're looking at a distribution that's a wave. Okay? And it turns out, because of the strange nature of subatomic particles, that particle sort of exists in all the points possible in that wave. So when we talk about an orbital, we're actually talking about its wave nature. And when you talk about that orbital, you're talking about its positional wave nature, or more appropriately, you talk about its energy wave nature. So to have that s orbital, it has to have a particular amount of energy. So every time you're introducing new particles, you're introducing new energies. Therefore, you get these new configurations of, okay? About the wave nature of matter. The other thing to understand about the wave nature of matter is it still behaves like a wave. So when we talk about constructive and destructive interference, talk waves in addition to electromagnetic waves, in addition to mechanical waves. So matter waves behave identical to all the other waves. I mean, there's a few differences. I mean, obviously we don't spend a lot of time talking about the amplitude of a matter wave. But we do talk about destructive and constructive interference. Okay? Cool? And actually that constructive and destructive interference is critical when talking about things like fermionic condensates and Bose-Einstein condensates. Okay?